And there are even more of them for M dwarfs. But the occurrence rate drops as you go inside of 10 days. There's a break, and there's a characteristic drop-off in the planet occurrence rate. Okay. And in fact, for solar-type stars, there's a nice extension of this data from an independent measurement made by Saul Rappaport, Al Levine, and collaborators who had their own independent pipeline to go after the ultra-short period objects. Okay, so why is there this break and this drop-off? Well, we think it's because disks, planets form in disks, and the disks are truncated, right? They don't go all the way to the stellar surface. They're truncated by the stellar magnetosphere. Stellar magnetospheres, they hold off the accretion flow when the ram pressure of the flow balances the magnetic pressure of the young host star. In equilibrium, that truncation radius settles down to co-rotation, where the disk is co-rotating with the star. There is evidence for co-rotation in these incredible Dipper stars, right? Dipper stars, pre-main sequence stars with disks that you're looking at just the right angle that you can see not only the star spots, which tell you the stellar rotation period, but also these wild dips, these flux dropouts, sharp, that happen with the same period to within 2 significant figures. The dropouts are from some blob dust in the accretion flow that's in co-rotation with the star, right? That's what's observed. And so if you believe in co-rotation, and this is what we assume, then the distribution of disk inner edges is just given by the distribution of stellar rotation periods. And there's this beautiful, over decades, people have measured painstakingly rotation periods of all kinds of stars, pre-main sequence stars in particular. You could even bin them in stellar mass. It's a beautiful data set. I think look at this cluster, right? Most of the stars are rotating at 10 days. There's a drop off from 10 days down to about half a day. This we want to map to the previous slide. This explains the planet occurrence rates profiles. That's the picture. And in this picture, you can imagine sprinkling your planets in the disk outside of co-rotation. You can distribute them in one of 2 ways, broadly speaking, right? You can either think, okay, well maybe the planets form in situ. In that case, I'm inclined to distribute them randomly, more or less randomly, in log period space. Log period because in oligarchies and these giant impact scenarios, the protocores are separated by a characteristic number of hill spacings, and hill radii are power laws. Or you think that migration has something to do with it. Okay, close-in planets, knee-jerk reaction is, oh, they must have migrated there. Well, if you really believe that, then the planets migrated inwards. They can't go past the inner disk edge, not by very much anyway, because there's just no material to torque them in further. And so they pile up. One of 2 things can happen. These trains of planets, they can lock themselves into mean motion resonance. Okay, that's one way. Or maybe the resonances are unstable. There's a lot of work that suggests that under certain conditions. They fly through the resonances, and then they have really no choice but to slam into each other. Okay, they merge. You're too deep in the stellar potential well to scatter out. Okay, they just consume each other. Okay, and in the lock-in versus the merge models, 2 different flavors of migration, they actually give you qualitatively the same result. And it's different from in situ. So let me show you that now. Okay, so just think there are 2 classes of model, in situ versus migration, and which one better explains the occurrence rate drop-off? Well, here's how well we do. Here's Fressin et al. Okay, here's plus Sanchez-Ojeda for FGK stars. We did this for M stars too. We did it for everything. Here's a theory for in situ, and this corresponding comparison for migration. Not great. We're missing the USPs, basically because we haven't seen pre-main sequence stars rotate faster than than half a day. So we're missing the USPs, okay, for now. I would say the migration models do somewhat worse in the sense that they produce an excess of planets relative to the longer periods, right? We're normalizing this whole thing so that the curves always run through the second to last point right up here. So, but there's an excess here for a very simple reason, right? Just because of pileups, just migration pileups, which is not really seen in the in-situ picture. We can do better for the USPs by folding in tides. So for the planets that are closest in, right near the inner disk edge, they're so close to their host stars that they can raise a tide on the star. Right? So the usual Darwinian, asynchronous equilibrium tide, and the planets closest to the star will undergo orbital in-spiral, just from tides. So it depends on the Q, I know, and the stellar dissipation. But for reasonable values of Q, we experimented. Here's how well you do. So you could do better for the USPs. Okay, you do better for you do better for the USPs for both the in situ and the migration models. But I'd still say this excess is still problematic for the migration picture. Okay, so I present this as an independent line of evidence in favor of in situ formation for super Earths. And here's just a summary. Here's how well we do. We sampled rotation periods from these clusters. These were the Q values we used. I don't think this is terribly controversial. And just to summarize, everything beyond here in the flat zone, in situ. Everything in here, also in situ. The reason why it's turning over is just because you're near the raggedy edges of protoplanetary disks. And then the ultra short period planets inside of about a day, well, there we invoke tides to bring them further in. So that's the picture. Yeah, Dave.
Do you have a free normalization parameter? Or is
Oh
it
yeah, no, sorry, yeah, absolutely, yes. We're not explaining, yeah, sorry.
You don't explain the higher rate of
we don't, yeah, that's right. We're just going after the shape here. The normalization, of course, is a super interesting problem. The fact that it's higher for M dwarfs versus FGK dwarfs, these are things that I'm currently thinking about and don't have an answer for right now. This is just a shape, this is a shape exercise. Okay, in the remaining time, I think I have maybe 10 minutes or so. Oh, I wanted to give you some predictions. So in this whole picture, we've talked about FGK and M stars. Well, what about A stars? A stars are different. A stars rotate faster. They also have magnetic fields, about 100 Gauss measured. So magnetospheric truncation, still relevant, I think. But they rotate faster, okay? Less magnetic braking. And so we expect the same rollover, right? Except that the rollover should happen at shorter periods because everything's rotating faster. So instead of rolling over at 10 days, we expect a rollover at 2 days. So one can only hope tests provide a sample of super Earths around A stars. All of this formation is pretty quiet, you know, nothing violent like high eccentricity migration and none of that violence. So they should have low Rossiter-McLaughlin obliquities. And again, spectroscopic follow-up of test bright targets, we hope to see small stellar obliquities for these close-in objects. And finally, there's a time dependence. Everything outside of about a day, all of this is established before about 10 to the 7 years. Everything inside of a day is established on gigayear tidal timescales. And so there should be, differences in planet occurrence rate and the shapes of occurrence rate profiles between young and old stars. And here I was really encouraged by, I think his name is Aaron Rizzuto at Texas, who's developing ways of detecting planets around young stars with their messy RVs and messy light curves, but he's going after these young stars, and I think that work is very exciting. Okay, so just some predictions. Remaining time, let me extend myself to gas giants. I'll bridge with sub-Saturns and talk about a particular subclass of sub-Saturn, which I think they're the most interesting, what we call super puffs. How can something which is only 2 Earth masses be as puffy as 7 Earth radii? Okay, the super puffs. They must have huge gas fractions. They're inferred from interior modeling between about 20 and 40%. They're rare, but they have these big gas fractions. Can we reproduce these? Well, we can, but we have to move things further out. Not near 0.1 or 0.2, 0.3 AU. We have to stage the whole theory now further out at about 2, 3, 4 AU. Why? Because the further out you go, the colder it gets. The colder it gets, the lower the opacities are, because you're just freezing out these rho vibrational degrees of freedom with these various molecules, right? You're just not exciting these lines. The opacity goes down when it gets colder, and therefore the luminosity goes up. It's just more transparent. And so the luminosity goes up, the cooling rate goes up, and therefore your accretion rate goes up. So it's just easier to accrete these atmospheres further out. So yeah, we can just make the cut for super puffs at about 2 AU, but not at 0.1. Okay, 2 AU, not at 0.1. This was just a little demo that Eve and I made. So, and